Hello everyone, I'm Zeinab Ashtab, a doctoral student in semester. The topic of my talking is about the Neumann problem on a torus. And at first, I'm gonna to talk about the toroidal coordinates. As you can see on my screen, eta is the logarithm of the distance between AP over PB. That A and P are foci and P is a point on the circle. And theta is the angle APB. And the angle phi is around the x0 axis. Also on x0 axis, eta is equal to 0, but here in this point that you can see by moving my mouse, eta is equal to infinity. The relationship between the toroidal coordinates eta, theta, phi, and the Cartesian coordinate x0, x1, and x2 is in this form. That here, eta is between 0 and infinity, theta is between 0 and 2 pi, and also phi is between 0 and 2 pi. And also, as you know that, the toroidal coordinates are not defined in these sets that I denoted by S1, the set of x in R3, that x0 is equal to 0, x1 square plus x2 square is equal to 1, and I denoted by R0, the set of x in R3, such that x1 is equal to x2, and both of them are equal to 0. I define for every fixed eta naught the interior and exterior toroidal domains. I denoted by omega eta naught the interior toroidal domains, and also I denoted by omega eta naught star the exterior toroidal domains. Solution to Laplace equation in toroidal coordinates. In the exterior of a torus that I denoted by capital E and M sigma tau of x0, x1, x2 is in this form. That here, Pn minus a half m cosh eta is the associated Legendre function of the first kind. And also the solution in interior of a torus that also I denoted by capital I and M sigma tau of x0, x1, x2 is in this form. Also here, Qn minus a half m cosh eta is the associated Legendre function of the second kind. Also, phi n sigma of tau is equal to cosine n theta when sigma is equal to plus 1, and it's equal to sine n theta when sigma is equal to minus 1 for every n and m greater than or equal to 0. A quaternion is an expression in this form that x is equal to x0 plus x1 e1 plus x2 e2 and plus x3 e3. That xi's are real number and e0, e1, e2, e3 are the standard bases of our form. By this formula, that e0 is equal to 1, ei square is equal to minus 1 for every I from 1, 2, and 3, and ej ei is equal to minus ej ei when I is not equal to j. Let a continuous function f be from domain omega eta naught to R3 in this form. We called f is left monogenic in an open domain omega if we apply the operator d bar in this form from the left side on f of x, and then we get 0. That also the multiplications between d bar and f of x is in this form. To calculate toroidal harmonics, I needed to figure out the derivative of capital I with respect to x0, x1, and x2. To do this and find the result for these derivatives in some terms of the same function, for the first step, I needed to find the derivative of this function. Then I needed to get rid of some prime of associated Legendre function. So I needed to use of sum of recurrence formula for the argument greater than 1 to get rid of this prime or some of the other associated Legendre function to get the some terms of the same functions for these derivatives. That's why after some calculations, I've used these recursion formulas for Legendre function for the argument greater than 1. As you can see here, for example, the equality number 1 and 4, there is a prime for the associated Legendre function. So it was very important and essential that to know which kind and which one of these formulas are convenient for our calculations to get the same function at the end. After a lot of calculations, we can have these tables. These tables is for derivative of capital I with respect to x0, x1, and x2. As you can see on the screen, the second line is the derivative of capital I with respect to x0, x1, and x2 when n and m, both of them are equal to 0 at the same time. Then we suppose that m is equal to 0 and we calculate the derivative of capital I for every n greater than 0. And then for n equal to 0 and for every n greater than 0. And the last line is for every n and m greater than 0. And as you can see here in this table, inside every cell are the same function. I mean, all of them are capital I. Suppose that the derivative of x with respect to eta is equal to x sub eta. The normal derivative of the interior toroidal harmonics that I denoted by norm of capital of I of eta, theta, and phi is equal to the derivative of capital I of eta, theta, phi with respect to theta, with respect to eta times 1 over norm of derivative of x with respect to eta, when eta is equal to eta naught. After calculation and simplify our expansions, we will have this expression which is in 3 terms and include phi n minus 1 sigma of tau, phi n sigma tau, and phi n plus 1 sigma tau. Given a continuous function f from the boundary of the domain omega eta naught to r, the Dirichlet to Neumann mapping that I denoted by lambda is described by finding the harmonic function u with boundary values f and then take the normal derivative that no u is equal to lambda f and it's equal to h. Suppose little q and m be equal to qn minus a half m push eta naught, only for convenience. Then consider the boundary function f, that we can write the function f in some terms of double Fourier series in this form. Then, according to the definitions of I, we can write f of theta and phi on the boundary of omega eta naught in these summations, in this expression. Define u in this form on the domain omega eta naught, summation of a and m sigma tau over q and m times I and m sigma tau of eta naught, theta, and phi. It can be shown that nor u is equal to summation of a and m sigma tau over q and m times nor I and m sigma tau. Then we can define the toroidal Neumann coefficient in this form, that I denoted this toroidal Neumann coefficient by kappa, lambda, and mu for all m greater than or equal to 0. We can simplify nor u. We say that nor u is equal to these summations of a over q times nor I and m sigma tau of eta naught, theta, and phi. If we substitute nor I that we calculated already here, so after some calculations, we will find that this equality is equal to this equalities, which is in 3 terms. A naught n, a n plus 1 m sigma tau, and a n minus 1 m sigma tau. And then it's equal to this expression, that this expression includes the toroidal Neumann coefficient that we denoted already by kappa, lambda, and mu. I mean, we defined already what is the kappa, lambda, and mu. So nor u of eta naught, theta, and phi will be equal to this expression. For any fixed eta naught, let f be a function from boundary of domain omega eta naught to r in this form. And suppose that the Fourier coefficient, which I denoted by a and m sigma tau, satisfy this inequality for some constant c. Then the Dirichlet to Neumann mapping, lambda f equal to h, is given by this formula. For all m greater than or equal to 0 and tau equal to plus or minus 1. And we can have these equalities that we denoted by b, coefficient b. B naught m plus tau is equal to this expression, b and m, for all m greater than or equal to 0 and n greater than or equal to 1 plus tau is equal to this expression, which is the summation of the toroidal Neumann coefficient that we defined already by kappa, lambda, and mu, and etc. To prove this term, according to the statement of this term and this equality, we have that the series, this one, of function f of theta and phi, converges absolutely and uniformly in theta and phi. Also, from this expression, these approximations, it follows that the expansion f of theta and phi equal to these summations converges absolutely, because the absolute value of capital I of eta naught theta phi over q and m is less than or equal to a square root of cosh eta naught plus 1. And the absolute value of norm I, capital I over q, is less than or equal to a constant C1 times n plus m plus 1. That this constant C1 depends on eta naught. Therefore, the absolute value of coefficient of a and m sigma tau times nor capital I over q is less than or equal to a constant C1 over n plus m plus 1 to the power 3, which this guarantees that the function h also converges absolutely. Then, by substituting nor I in this expansion and then reindex phi n theta, phi n minus 1 sigma tau and phi n plus 1 sigma tau into phi n sigma tau, then we can obtain these equalities for function h of theta phi. As you know that the Neumann problem is given a function h, find the function f so that lambda f is equal to h. Also, compatibility condition says that if integral of h on the boundary of domain omega is equal to 0, the Neumann problem has a solution unique up to adding a constant. So we can say that the compatibility conditions on function h, if we apply, if and only if, this expression will be equal to 0. In other words, if the double integral of h of theta phi on the boundary of domain omega eta naught is equal to 0, if and only if this expression will be equal to 0. That here epsilon n is equal to 1 plus omega n 0. We can prove these propositions by using the fact of Cole and Domnich's article in 2010 to calculate this integral. I mean, the first integral here with respect to theta, which is cosh eta naught minus cosine theta to the power minus 3.5 phi n sigma of theta. We can use the fact of this article and prove that this is equal to 0. To calculate and talk about the algebraic solution, at first we need to know that mu and m for every n greater than or equal to 0 are never 0. We can prove these propositions. It's clear that mu 0, 0 is not 0. Also, it can be shown that by using of these equalities, according to the Hobson's book in 1931, minus 1 to the power mq nm cosh eta is greater than 0 for all n, m, and eta. And then we can apply some of the recursion formula that we talked about that already, and we can say that mu and m are never 0. Given a coefficient b and m plus tau, then we can have these equalities. Let A0m plus tau be equal an arbitrary value that I denoted by A, and A1m plus tau be equal to this expression, and etc. Then define capital AN of A, which is equal to ANM plus tau, by means of this expression. A not of A is equal to A. Therefore, by a simple induction, we can have a linear expression in this form, that AN of A is equal to CNA plus DN for all n greater than or equal to 0. As you can see in the screen, that after some calculations, we can say that C0 is equal to 1, C1 is equal to minus lambda naught over mu n, over mu naught, and etc. Also, D naught is equal to 0, D1 is equal to B naught over mu n, and so on. But the calculations of this capital A sub n of A is not usually a solution of the Neumann problem, because these summations will converge for only one value of A that we denoted by A opt. If n tends to infinity, so an of A opt will go to 0. Therefore, CNA opt plus DN will go to 0. So, if we can assure that if n tends to 0, so Cn will go to infinity. So we can say that minus Dn over Cn will go to A opt. That was all that I want to talk about that. And at the end, I want to say thank you very much for your time and for your patience.